So in many instances in engineering and science, you're going to be required to calculate estimate intermediate values between precise data points. And I'm going to show you some methods to do that now. And we're going to first look at Newton's divided difference for interpolating between polynomials. So that's important. We're going to exploit the fact that a function can be expressed as a polynomial. All right, so Newton's method is popular and very useful, and there's a general equation for it, but before we get onto that, we're going to first explore the first order and second order versions of that equation. Okay, so the first order version can be explained quite easily using a simple graphic. So let's say we have a function that looks something like this with curvature in it, and we have two discrete data points in our function. Okay, so linear interpolation says that if I wanted to, let me just mark this up. So let's call this data point x1, x0, that obviously corresponds to fx0. Now remember, we don't know what the function is. I'm just drawing it in between these two data points. And fx1, and I'm going to call an intermediate point here. Let's label it x. I'm going to say f1 of x. Okay. So if we connect these 2 points, x1 and x0, we can use similar triangles to figure out a linear interpolation that explains our function. So we can say this similar triangle and this similar triangle can be exploited so that f1 of x minus fx0 divided by x minus x0 is equal to fx1 minus fx0 divided by x1 minus x0. Now we can rearrange this to get our first order approximation, that is f1 of x is equal to fx0 plus fx1 minus fx0 divided by x1 minus x0 multiplied by x minus x0. Now obviously this is a linear interpolation, so the closer x1 and x2 are, the better our approximation is going to be. But there's often large areas associated with this because we're approximating, say, a curve with a straight line, and this is simply not going to do the trick. So let's look at the second order version of our equation. So this strategy now tries to introduce some curvature into our approximation to account for any nonlinearity in our actual function. So we're going to introduce a quadratic fit, but in order to do that we need 3 points, x1, x2, and x0. So we can write our second order version of Newton's method as f2x is equal to b0 plus b1 x minus x0 plus b2 x minus x0 multiplied by x minus x1. We can gather these terms to say that f2x is equal to a0 plus a1x plus a2 x squared, so that a0 is equal to b0 minus b1 x0 plus b2 x0 x1 a1 is equal to b1 minus b2 x naught minus b2 x1, and a2 is simply b2. Now, how are we going to solve for our unknowns? Well, if we set, for example, x equal to x naught, immediately we cancel out our second and third terms, which means that if x is equal to x naught, so at that location, the function value, or our data point in this instance, f2 at x naught equals b naught. Now we can use this at our next data point, which would be x being equal to x1, and then we could calculate b1 such that b1 is equal to f x1 minus f x naught over x1 minus x naught. And similarly, it's clear here, at the point x equals x2, b2 is going to be f of x2 minus f of x1 divided by x2 minus x1 minus f of x1 minus f of x naught over x1 minus x naught all over x2 minus x naught. And so from looking at the first and second order versions, we can start to now look at the general form of our equation. So now the general form of Newton's method is f of n of x, where n stands for the order of the polynomial, is equal to b naught plus b1 x minus x naught plus bn times x minus x naught x minus x1 all the way to x minus x n minus 1. And as before, b naught is equal to f at x naught, and b1 is equal to f square brackets x1 x naught. Square brackets are now indicating that I'm using the data point, and bn is equal to f xn minus 1 all the way to x naught, where our square brackets f square bracket xi xj is equal to f xi minus f xj divided by xi minus xj and then I can say f of xi xj xk is equal to f square bracket xi xj, which is simply what we saw before, minus f square bracket xj xk all over xi minus xk, so that f square bracket xn minus 1 to x1 x0 is equal to f square bracket xn n minus 1 x1 minus f xn minus 1 to x0 all over xn minus x0. Just take a second to look for any patterns here, because it's going to become apparent in our next formulation, which is that f of nx can be written as f x naught plus x minus x naught f multiplied by f square bracket x1 x naught plus x minus x naught multiplied by x minus xn minus 1 multiplied by f square bracket xn minus 1 all the way to x naught. Look familiar? Well, if f square bracket x1 x naught is simply f x1 minus f x naught over x1 minus x naught, we can start to see the Taylor series coming out again. So let's reinforce this with a problem.